Intel uses our second generation of high-K metal gate transistors. We've already reached yields on this technology that make it very production-worthy and moving into high-volume production. In fact, we've started production on the first microprocessor on this generation of technology, codenamed Westmere, for shipments to our customers in the fourth quarter of this year. Now, we're not stopping at 32. We've been working on a new technology, the next generation after 32, which is 22 nanometers. And I can't show you a picture of this transistor here because my guys just won't let me. However, I can show you, for the first time ever, the world's first working 22 nanometer silicon technology. And if it's not able to show you, it also works. It's the smallest SRAM cell ever invented. These transistors use a third generation of the high-K metal gate technology. Each SRAM chip has 2.9 billion transistors. Each array on the SRAM is 364 megabits. It's on track for production, second half 11, continuing our 2-year cadence. At Intel, Moore's Law is alive. A new microarchitecture on an existing silicon technology, which we call a TOC, move to the TIC by shrinking to the next generation silicon technology, and then moving to a new microarchitecture, a shrink, and so forth. And we've done this for many, many generations in a row. This continues with this generation. I talked about 32 nanometers in the Westmere product, which has a new scalable architecture, a number of new features that we're very excited about, including one called Turbo that Sean and Dottie will discuss in their keynotes. But beginning with this generation, graphics has also now been integrated into the microprocessor. Looking forward to the next TOC on 32 nanometers is Sandy Bridge, our next generation microarchitecture that will be out on cadence late next year. And looking forward into 22 nanometers, we already have significant design work on the processors that will take advantage of the silicon technology I just showed you on that width. But recently, we've introduced a second architecture that's not based upon the core products, but around Atom. And this is a microarchitecture focused on using our best technology, best silicon technology, to design the best products for internet-connected devices. And we now have the ability to deliver these devices on a predictable cadence, essentially generating roadmaps that you, our developers, can count on. You can see them here, 2-year cadence, a new core coming out about every 2 years on different silicon technology. The tick-tock cadence here is slightly different. What this really reflects is Intel's traditional pattern of innovation and integration. We'll use these new cores on successive generations of silicon technology to do proliferations of what we call SoCs, or system on chips. SoCs are a very big investment for Intel. We think that SoCs based upon the Atom core are what allows us to be able to move into all of the new markets that we'll be discussing in a few minutes. In addition to building these devices at Intel, we've also announced that we're porting this Atom core over to TSMC. And in doing so, we're rewriting the traditional rules of how Intel has operated. We're not doing this for capacity. We're doing this to be able to reach out to new customers, to allow customers who want to embed their own intellectual property onto an Atom core SoC, or to use the wide variety of library devices, I/O devices that exist at TSMC to build semi-custom devices around it. Been able to fill in the gap that would have ultimately, without it, had led to a down year, I think. I'm comparing here the first 6 quarters of shipments of the 3 hottest consumer electronics devices in the last 3 years: the iPhone, the Wii, and the netbook. And the netbook has outpaced all of these after the 3rd quarter, and there's really no looking back. So as we look at the opportunity around netbook volume and how to accelerate that even faster, one of the things that becomes very clear to us is that we need a better applications environment. These devices, as Art pointed out, are ultra portable. People want to do more on them than just running legacy applications. There are areas where we compete with Qualcomm, there's areas that we cooperate with them. It's a classic cooperation model. We're helping them with their Gobi modems, 3G modems into our notebooks and netbooks. You know, that we're doing that because it makes good business sense. They have some products that compete with us, but they also, in general, are communications focused for most of their business, and we are compute focused for most of our business. So the opportunity to cooperate, I think, going forward is large. And I wouldn't necessarily draw this as one of those epic business conflicts.
Phil, this is the first public demo of our new baby. Maybe you could tell us a little bit about it.
Yeah, so it's a great baby. I'm really excited to be able to talk about it. So what we're showing you here is an application that demonstrates some of the flexibility of Larrabee. And it's running on the Larrabee software development vehicle. So this is the early silicon. And it's also got some other Intel goodness in it. It's got an Intel Gulftown CPU. So what I'd like to talk about is what makes Larrabee unique. Right? So what makes Larrabee unique is you get a fully programmable rendering pipeline. So this lets you, in addition to standard DirectX, OpenGL, you can also implement customized rasterization pipelines. And maybe even more interestingly, things like voxel rendering and ray tracing. So if you look up on the screen here, so this is the demo running live. And this is a ray tracing demo, right? So what we did is we took content from Splash Damage and id Software. So it's the game is called Enemy Territory Crate Wars. We took that content, the textures and geometry, pulled it out of that game, and put it into our ray tracing engine. So ray tracing is a well-known technique, but traditionally has not been used in real time. So now we've got it running in real time. And what makes it special is that it allows you to simulate the interaction of light with matter in a way that's accurate. It makes it really easy to get effects like shadows and reflection and so forth. So as an example here, if you look at the water, you see a nice reflection. And that's done with only 10 lines of shader code. It would be a lot more difficult to do in a conventional game engine. For programmers, what's interesting about Larrabee is not just the flexibility, but also the ease of development. And so let me just give you a specific example of that here. So you see there's some moving objects in the scene. There's some helicopters actually temporarily to the left side of the back. And that's traditionally difficult in a ray tracer. But what we've done here is we rebuild some of the key data structures every frame on Larrabee using a form of parallelism called task parallelism. And so what this is really showing is that you can do the same kind of things you do on multi-core CPU, but with even more.
Do you have like a video connection like HDMI or something? I saw that on one unit. I couldn't remember which one, where I saw that. That's in the larger one.
Second generation, there's a VGA function.
VGA right there.
Yeah, yep. Right here. And the standard USB and 3.5 audio jack.
All right.
Yeah, second generation will be available like the end of this year.
Right. So this is just the mock-up, but these are already on the market then,
sure,
right?
Yes.
Looking at some of the very small handhelds that have HDMI. It's real interesting because you can process the video from the little tiny platforms. I like that. So very good. Is this already? Is this a demonstration model, or is this already on for sale?
Already sold. It's online and offline.
All right, fantastic. So look for that prize. Thank you.